So the van der Waals systems are an excellent laboratory for thickness. So part of the main goal of this conference is the limit of two-dimensionality in superconductors. And the van der Waals materials allow you, usually a posteriori, to tune the number of layers. This is tantalum sulfide in this cross-section TEM image. 1, 2, 3, 4. Here you have about 20 layers. You can identify the polytype. You can count the number of layers. And this gives you some level of control over what is the thickness, and can look at what the thickness does in superconductivity. And our main tool of research in our lab is this tunnel junctions. So we fabricate the devices generally like that. This is a superconductor. We transfer a tunnel barrier on top of the superconductor. So but in this case, we're looking at tantalum sulfide, and here the barrier is molybdenum sulfide, but it could be, the superconductor could be just as well niobium selenide, or any of the other polytypes, interesting polytypes of these TMD materials. And the barrier could be any of molysulfide, molyselenide, tungsten sulfide, tungsten selenide, sometimes HBN. HBN is a bit harder to work with. But what I want to call your attention to the following thing is, look at this interface. So here you see the atoms, here you don't see them. It's just a matter of the orientation of the crystal versus the point of view of the detector of the TEM, but you can see that the contact is perfectly atomic. And this is because these TMDs on TMDs, they engage very, very cleanly, and this gives you a very clean, very well-behaved tunnel junction. Now, tunnel junctions, you heard a lot, many talks by STM people, but tunnel junctions supposedly is just sort of a poor man's version of STM because the electrode is fixed. But there's several advantages you can gain if you work with a fixed electrode tunnel junction. One is you can have very effective filtering. So you can have higher energy resolution. Another thing is you can usually work with high in-plane field, which is very hard. Usually STMs don't have very high in-plane magnetic fields. A third thing is, this is not working now, you can actually run currents through your devices and couple tunneling electrodes. And you can get very, very fine electron energy resolutions. I'm going to show you later. You can get few micro electron volt resolution in your energy reading. And that allows you to track all sorts of effects of depairing versus current versus magnetic fields. So this is a project that's been running all over the years. We're here in Orsay, so I have a huge debt of, scientific debt to the people here, to the teams of Caris and Marco and Hélène and Sophie. So I reached out to this group over 10 years ago, knowing this is the place to learn superconductivity, and this is the place to learn how to do tunneling measurements, and we've been having a very fruitful scientific relationship over the years. The results shown here, the theory done by Jonathan Ruchman from Bar-Ilan University, and his postdoc Gennady Yerzhekov, and by Maxim Chodesh from Hebrew University. And we had a lot of help from Oded and Amit Kanigel from the Technion. Also some provision of some samples and data. So yesterday, Tristan presented the TMD superconductors. So I'm not going to go into an exhaustive introduction. What I have to show is just that these are materials that are the single layer break inversion symmetry, and one of the results is that there is a very strong built-in spin orbit term, and the way one can understand it is if you travel along a certain trajectory, there is a built-in electric field, and if you have a built-in electric field, which is the gradient of V cross P, that creates a very, very strong out of plane effective spin orbit magnetic field, and this stabilizes the Cooper pairs out of the plane. So about 10 years ago, there was a lot of interest in the thin limit of these TMDs, and the Kufkin-Feimak published this particular paper in 2016, and they showed that if you go from bulk niobium selenide, which has TC of about 7, you go thinner and thinner and thinner, you can reach monolayer. And this is actually one of the very, very few studies that people report that on monolayer niobium selenide. They measure a TC of about 3 Kelvin, and they track the decreasing TC. And this is not such a great surprise. They cite some papers, various theory papers, saying basically superconductivity grows weaker. You have a fewer phase space of theory. And indeed, nobody is very surprised. And if you apply very high magnetic field, you get this strong Ising protection stabilizing your Cooper pairs, and if you can extrapolate your result to very high HC2. In fact, nobody really measured HC2 because theory kind of is kind of open about what really happens here. And you can see in Kinfine Max data, they only reached like here. People reached 30 Tesla, but it could be even higher. Neither on HC2 nor on tantalum sulfide. But the bottom line here, for the purpose of my talk here, is that I can say the following thing. As we go to the ultra-thin limit, Ising superconductivity takes over, and you can have a very strong stability against in-plane magnetic field. If you go thicker, you start having orbital depairing, so this whole effect disappears and the HC2 goes lower. But there are many other things that happen with thickness. As you see, also this block here is still empty. So let's go to the second thing. About in the beginning of the week, we had a talk by Ding Zhang, and he showed some data from his group and also from the group of Justin Ye from Groningen. And what they show is that there is an effect that kicks in at about 10 nanometers, and this is called the orbital FFLO, and that seems to be another phase at a higher magnetic field, which the groups working on this field associate with a different kind of Cooper pairing involving a momentum degree of freedom between adjacent layers. And this phase appears only at the thicker limit of over about 10 to 15 layers. So you have Ising at the ultra thin and FFLO at a thicker regime. And then there's other stuff. Yes?
Can I ask what is on your horizontal axis? Will you disclose? So in your graph that you have before?
Yes, I've been talking only, those are just different effects here. This is not like some kind of a quantitative thing. So I need space to show things. So it doesn't have any physical meaning. Thank you for asking this, Elke. Okay, so this is data. Now I'm citing data that we took right here from. It was back with my first PhD student, Tom Phil, and we were looking at mid-thickness, 20 to 30 nanometers niobium diselenide, and we found that if you look at the spectrum of tunneling spectrum of niobium diselenide, we start cranking up the magnetic field. You see actually that the superconductivity includes two gaps. This is the first derivative, this is the second derivative. And they evolve differently with the in-plane magnetic field. So you can look at these two spectral features. This different evolution has to do with how they depair due to the presence of the Meissner currents. And that was work we published together with our Orsay colleagues about 10 years ago. And this whole thing is based on the fact that niobium diselenide has two gaps. And so, yeah, you could see that if you go from 50 nanometers to 20 nanometers thickness to below 10 nanometers, the two gap feature disappears. And I will always say, okay, we go from two gap to one gap. And it's one commonly associates the second gap with a selenium pocket, which as you go thinner, the selenium pocket disappears. Now, recently, we figured out that this is wrong. This is actually not 2 to 1, it's actually 3 to 2. That ties back to a discussion that was held yesterday in the talk of Tristan. This is the spectrum of NBAC2 as 30 layers, 20 nanometers. You clearly see here two spectral features, and it fits very well with the Macmillan model of two gaps. But notice this coupling term, which is a term of scattering between the two gaps. It's about a fifth quarter of the bigger gap. Recently, Shachar, my student, figured out that if you look at the spectrum of niobium diselenide, you have a problem because everybody tries to fit this data to BCS, and it doesn't work. It only works if you fit it again to the same Macmillan model, but then if you look at the two gaps, you have a much greater coupling term, and you understand this by the coupling term, the scattering term being greater than delta, or the order of magnitude of delta. And this was recently accepted, published in PRL. And what it actually shows you is that even if you go to the thin limit of niobium diselenide tantalum sulfide as well, you still have multiple gaps. But we think you have two gaps in the thin limit, which are niobium or transition metal gaps, and another gap, which is a chalcogen gap, adding in niobium selenide as you go thicker. So what we can claim here is that 3-band goes to 2-band at about 10 to 20 nanometers. So you go from 2 bands to 3 bands. That's one more thing that thickness controls. Okay. Another thing is, this is another work I did together with the team here in Roset. Was exactly 8 years ago, and I was watching the World Cup as I was taking the train up to Grenoble, like on my phone, and we were measuring it very high in plane magnetic field, and we saw that there's an excess stability which develops at the high magnetic field, and we argued that this has to do with the supposed spin triplet component at this high field. And for some reason, I didn't write it up here in this thing that I prepared 2 days here. Now, this is all stuff that was done in the past. And I'm now going to go into the more newer stories. And that's a question of what happens in niobium selenide and tantalum sulfide and how TC evolves. So I'm going back to this data by Kinfei Mak, and as you go thinner and thinner and thinner, you see TC going down, and again, nobody was very surprised. But let's see what happens in tantalum sulfide. The data looks very similar, but I want to draw your attention to the fact that the bulk is this guy and the monolayer is this guy. So the bulk is 0.8 Kelvin, and as you go thinner and thinner and thinner, TC goes up. This is data. These are actually 2 data sets, one from the group in Valencia and the other from Pablo Javier, and you see TC going up. So if this is the same mechanism as niobium selenide, so it's just not coupling made easier by having neighboring layers, because things work exactly the opposite way. This is a compilation of the two materials, niobium selenide going down, tantalum sulfide going up. And this paper by Yafan Yang from Pablo's group, they argued that there is a role to charge density wave, showing that this is a charge density wave effect on the bulk, and as you go thinner, the charge density wave goes weaker. So they raise the possibility the charge density wave somehow suppresses superconductivity. So and if you look at this curve over here, this is a DFT calculation that they presented. They say you gap out part of the Fermi surface, so superconductivity goes weaker. Okay, so where is there any relation between the mechanisms and the two materials? Well, this is where we come in. So let's just take another look at our data here. We built tunnel devices. This is bulk niobium tantalum sulfide. You see the gap's really small. It's about 100 microvolt. And you go to a wider and wider gap in the monolayer. You have about closer to 500 microvolt gap as you go into the monolayer. We had only one monolayer device. If you ask me what are these shoulders, the answer is I don't know. I only solved them once, so I can't give you any responsible answer. It will be nice to make another device. It's a bit painful because you have to look for a monolayer. So that's again this nice TM intersection done in our nano center in Jerusalem. And then we can do some quantitative work and see how various parameters are affected by thickness. For example, we can look at the critical temperature. We measure tunnelings. This is how we measured the TC. We just track the G naught right here at the center of the gap. This is bilayer and 4-layer and 20-layer. And we can extract the delta versus the number of layers. See what's the number of layers. But I want to draw your attention to something here. If you look at transport data, these are the red data. So people were looking, okay, TC goes down, 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 bulk. And they saw, they called all these guys bulk. We think they missed something, because if you look at our data, you can see that at 30 layers with about 120 microvolt, and from 30 to 10, you actually go by a factor of 2. So this is quite interesting. Tantalum sulfide has a huge, very, very fine control over delta as you go all the way up to like 30 layers. So it seems to be that this 2D to bulk is much more gradual in this material. I think this is interesting because it gives you a very, very nice knob of tuning superconductivity. But that's not the whole story. If you look at delta versus TC, of course, you have a very nice relation which agrees perfectly with the BCS slope. This is the in-plane magnetic field, Ising, no surprises here. But let's see what happens when we look at out-of-plane magnetic field. This is bulk. We increase magnetic field. We reach HC2 at about 80 millitesla. But what surprised me was the fact that as you go to to the thinnest limit, HC2 goes way up, over 1 Tesla by a factor of about 10. So we do all these compilations, number of layers, you see about an order of magnitude increase, and then we plot HC2 versus delta square. We got more or less something like a linear relation with a bit of a sort of outlier points here at the 1 to 2 layer limit. Now, this is a bit of a surprise, and I'll explain why. Because in according to Landau-Ginzburg theory, you're supposed to be inverse to psi square. H2 is inverse to psi squared. Psi in Landau in the clean limit is proportional to the BCS side, and which is inverse to delta. So if you were in the clean limit, everything would be really nice. You have this relation which depends on VF squared, and He2 should be proportional to Tc squared. But the problem is that tantalum sulfide is not in the clean limit. So this relation shouldn't hold. So we see a relation which shouldn't hold, but is holding. So the next question that we asked ourselves was, okay, let's plot it on a log-log plot, and let's add the niobium selenide data, because this data is there. All we need is go and reach out and find it. So we took it from Kinfei Max's paper. This is the same paper I keep citing, and this is the data we defined. This is bulk niobium selenide, Hc2. It's in Kinfei's paper. You go down to a monolayer. This is about tantalum sulfide. As you go up in Hc2 and Tc, and they meet at a monolayer. So they all seem to sit on one curve. But that's not the whole story yet. Let's see if there are other materials in this family. So one interesting material is tantalum selenide. So there's this one paper from about 25 years ago that they measured extremely low Hc2, about 2 millitesla, and very low Tc, about 130 millikelvin. So this one paper adds this data point. But this data point sits right at the continuation of these. These are later data sets from people who actually built devices on tantalum selenide. There are very, very few data in the literature. And this is niobium sulfide. So all these four materials sit on this one curve, which spans 4 orders of magnitude in Hc2 and in Tc squared. And again, supposedly this is a relation of a clean superconductor, but these are 4 different materials. We go from clean to dirty and clean, dirty to clean again. So it doesn't seem to fully depend on this question of whether it's a clean or dirty superconductor. So of course, we can't just let this data sit there without setting up a theory. So of course you know that all these materials have a very, very similar band structure. So what could tune the superconductivity? Together with Jonathan and his postdoc, we suggested that this is actually charge density wave. So they did a very, very kind of powerful muscular calculation, looking at the band structure, adding charge density wave, calculating Tc based on Ginzburg-Landau theory, calculating Hc2, and finding this result. Now, okay, you get the same very nice curve, but the values are all wrong. And the values are wrong because you assume this relation which depends on V Fermi, and if you extract V Fermi from our data, you get the number 3.2 10 to the minus 4, which is a wrong value. No data set on TNDs give you such a slow Fermi velocity. RPES and DFT and any kind of measurement that you get gives you about between a factor of 3 to a factor of 10 faster V Fermi. So what this means is that this formula is wrong. Now, what is the correct formula? The answer is I don't know. That obviously this theory is good for describing how charge density wave suppresses superconductivity, but it misses something fundamental on how superconductivity evolves in these materials. So this is, as far as we are concerned, about the question. So back to my curve here, my map here. In niobium-based materials, Tc goes down. In tantalum-based materials, Tc goes up, and we're not entirely sure why. So since I'm about 1 minute from the end of the, maybe how many minutes you give me? You're the chair now. So 6 minutes. How? 6 minutes, 6 minutes including question, right? Okay, so I'll talk 3 more minutes, and there's one more thing I want to show you. So there are vortices. So I'm going to skip the part where we do tunneling of vortices. This is work done by Shachar Simon and Maya Klang, my students. Maya is now in ETH. And we were able to do Doppler effects of rearrangement of draining current using a tunnel barrier. This is now under review, and I'm gonna skip that. What I'm gonna show you is data that we took have a long skip to do here. This is probably 10 minutes of a talk. We were looking at samples which were at the 10 to 15 layer range, and we were looking at vortices which we could detect because their per length was very, very long. The effect at the ultra-thin limit of the rearrangement of current due to vortices can be noticed a very large distance away. So it would be really nice if we can measure the vortices directly, and that's why you need to have friends who have a scanning squid. So you have some people here who do scanning squid for a living. In Israel, you have a few of these labs. I worked with Yoni Anaholi, who has the squid on tip. And the squid on tip is a very, very locally precise probe. And this is work done by Moran, Nofar Friedman, published last year. And what we find in this work is the following thing. We sandwich NBSC2 between two HB, and so it's really, really clean, and you don't have contacts. And you look at various regions in the NBSC2, you can see you can count the layers, the thickness very, very precisely after you measure, post-mortem. And we look at the size of the vortices using this tuning fork vibrating squid on top, and you can actually extract the lambda per length defined by this measure, one by one for all the vortices. And what we find that if we look at the thicker limit, we get 1 over d, which is expected for a Pearl vortex. And then something really weird happens when we hit 6 layers. You see that the size of the Pearl length jumps by a factor of 3 to about 100 microns and stays there. So 6, 5, 4, 3, you have the same Pearl length. And nobody saw such a transition in any other measurements. On NBSC2, we were measuring tunneling. We haven't seen any such result on ultra-thin NBSC2. KINFI's data on transport hasn't seen any such result. It only shows up in the squid on tip. So we don't know why it only shows up in squid on tip. We proposed a model that it's related to a surface effect, because a surface effect would be insensitive to thickness as you go to the thin limit. So the big mystery is, where has it been until now? And what does it actually mean that you have something happening on the surface? Maybe the sample is cleaner. I don't know. I think also Kinfei Mak and Justin Yeo know how to build very, very clean samples. So what we see here in this map now is that in addition to all the other effects, something shows up which could be surface dominated precisely below 6 layers. So this is the last slide here. It's 957. So the many rows of thickness are the following. We have an increase of Ising stability. We have an onset of FFLO at above 15 layers. 3-band spectrum below 10 to 20 nanometer goes to 2-band. There's an onset of triplet at very high in-plane field at the ultra-thin limit, which is also related to this Ising. And there's this change of TC and HC2 along an universal ratio, likely through charge density wave, and this transition below 6 layers, which sounds big. And my final question, which is going to be the final thing I'm going to say in this talk, is, are these all independent changes? Or could some of these 6 different things be the same physical effect, which is just manifest in 2 different measures? So the answer is this. I think it's an open question for the community. I think the bottom line is that these materials are complicated. They are, everybody who works in ONK is laughing at me now because I saw yesterday what's a really complicated material. So sorry, they're almost maybe not as complicated as a 58 atom unit cell, but TMDs are a complicated material system, and every time people dig further, more stuff shows up. So that's it. I'll leave you with this observation.
Both minutes of questions. Yes, Anashi.
So this is regarding the fact that you have the tantalum is like the TC shift in 2 different directions in number of layers. Is there any correlation with the carrier density and mobility in the normal state?
So carrier density, to the best of my knowledge, doesn't really change very significantly. You have very high carrier density, about 10 to 15 per square centimeter, in the per monolayer. I don't think it, based on what it's a bit hard to tell because you have to measure like RPES to see the Fermi surfaces, and RPES is very hard to do.
I mean, just all
And the transport, I don't know if things were measured that systematically versus thickness. It's not so easy because you have to do whole probes at these various thicknesses. Transport, again, to the best of our knowledge, there is a reduction of scattering. So scattering transport goes poorer as you go to the thin limit.
So your conclusion about 3 gaps, there is something that I missed. You see 2 gaps in the spectra clearly.
Yeah.
The third gap, you say it exists, but because of interband scattering, it's not visible directly
Exactly.
in the data.
Exactly. Yes.
That's
The reason is, I didn't want to go too much into the technical details. The reason is if you try to fit Dine's model BCS, it simply doesn't work for these materials. If you try to fit anisotropy, it doesn't work. So you know, it's a bit of an Occam's razors, like the more and more parameters you add, the better is going to be your fit because you just have more tuning parameters. Macmillan is a plausible model which works very well. It could be working well because it has no free parameters, but it works very, very well. And I think Tristan, you also showed data which was actually looked very much like ours and also fit very well.
I see, but your 2 gaps, the one that the second spectra that you showed, the 2 gap, one of them was 0.27 or something.
Well, 0.3 and 1.2. 0.3 and 0.3 millivolt and 1.2 millivolt.
But the coherence peak feature is
The coherence peaks is around 1.1. Yeah. And I agree with you. It's a bit of a surprise, but if you crank up the coupling parameter, it's like one overtakes the other. There's another point which it didn't go into the point because the density of states actually is important, and we assume that it's K and gamma, and one has double the density of states of the other, so it's more dominant. So it has a stronger effect on the total density contribution.
But would you call that so if you have such a strong interband scattering, would you call that an effective one band? I would sort of think that it's effectively a one
You
band.
may be right, but then you don't get one band is BCS, and BCS gives a much taller quasi-particle peaks. So in a way, our attempt was trying to explain why there are lower quasi-particle peaks.
Any reason why, at least in the thin layers, you can dope the system in the gate? Any reasons why you don't do that or study it as a function?
So you're asking
About displacement field and gate potential.
okay, people did some gating. It's very hard to gate because the density is 10 to the 15, and it's very hard to tune 10 to the 15. And it's from Kinfai's group that it is a bit around it. And so you get, I think in this particular case, is that all of them have the same density, more or less. If you move the density, things are going to change. EC changes and HC2 changes. But there are people who did liquid gating. There's a lot of data from Orpergo. It doesn't sit on this curve. It sits on a different. Omnemo is too. And if you do gating, it's not. So we tried that. We looked at other people's more liquid gating.
The last question from Christoph.
I'm very confused about this jump in lambda. Is there any explanation why the bulk should not see it?
So it's a very confusing effect, and the theory that we suggested there was that there's basically a competition between the surface and the bulk, and both basically what you have is that at some point there's a different order parameter on the surface that sort of takes over, and the advantage of this theory is that it allows you to explain why do things remain fixed below 6, and why, because then there's like the surface becomes much more dominant. And the disadvantage of this model is that it should have been seen in other same effect. So that's how I'm concerned about.